Let's work another example. So I'm basically calling this lecture 3/lecture 4 example. And this is example number 2. Okay. So example problem. We've got an electric car. Again, you don't always have to write out the entire problem statement. I'm going to do it here. An electric car consumes 380 BTUs of energy to accelerate a car with mass of, let's say, 1,800 pound mass. So not a real heavy car, probably unrealistically light. And I'll be honest with you, these are not real numbers for some real cars. So if you own a Tesla, like, well, that's not real. And yeah, I know it's just an example problem. I'm being very clear. I'm not claiming this to be real. So we're gonna can accelerate a car with a mass of 1,800 pound mass from rest to a speed of, I'm going to use a weird number, 328,000 feet per hour. I thought about leaving that in miles per hour, and I thought, no, it's fine. I think it's around 60 miles an hour, give or take. So it's from rest to a speed of 328,000 feet per hour on a level road. I don't know why I drew one cursive L and one regular L. Determine the efficiency for this process. Okay. So we're going to find the efficiency. What's given? So standard for problem solving procedure says, what am I looking for? You're looking for the efficiency. Okay. What do I know? Well, all right, let's organize what's known. I know that it's consuming the energy consumed. What do we call that? Well, I'm just going to call it energy consumed for right now is 380 BTUs. Sometimes it's not clear what's given to you, what to call it. How do I put it in my language for not my nomenclature? Sometimes it is like this is easy. This is the mass. Okay, that's M. M is 1,800 pound mass. But sometimes you'll have very important information. I can tell you this is true when you're working with, as an engineer out in the field, you're working for a client, for your manager, you'll have information that you need to record, but you don't know how to store it yet. You know you need to capture it. That's what this is. I'm not sure what to do with this yet, but it's an energy value. We know it's important. We'll figure out what to call it as we go along. From rest, that's important. V1 is the to a speed of 328,000 feet per hour. And we're doing it on a level road. Z2 is equal to Z1. We want to find the efficiency. That's what we're looking for. So this is what we're looking for. This is what's known. The next step is what rules, laws, or equations might help us find that. Well, I'm looking for efficiency, so I need to look at, well, okay, well, how do I find efficiency? Well, efficiency is often, your text will say it's the output over the input. And I don't care for just memorizing this as a formula. It's okay to think of it as a concept. I mean, just kind of be careful with that. Again, we were often taught, think about what's going on with the situation and think about what do you expect to be the smaller value divided by what do you expect to be the larger value. You're comparing two things when you do an efficiency. You're comparing two different things. Output over input sometimes works just fine. I think we could actually make it work in this case, but it really is what do you expect to be the smaller quantity and what do you expect to be the larger quantity? Well, that's where this comes in is what is this, right? What is this? This is the energy that this car is actually consuming. Do we expect that any car, I mean, we could take gasoline, for example. Let's say, do we expect that a gasoline powered car it burns more energy than what it can actually effectively use? Well, yes, we've done a really good job of getting as much efficiency out of those things as we can, but they're not 100% efficient. Nothing is. So we expect that it's going to emit a lot more energy in burning the fuel than what it's actually going to turn into work. And the same thing with an electric car. It's not 100% efficient. It's going to use energy out of its battery more than what's actually going to make it do what it's doing. What's it doing? Well, it's accelerating this car. So we expect that the energy required to accelerate is actually going to be less than the energy that actually gets consumed. So the efficiency actually kind of ends up being the work in required divided by the actual energy this thing consumes, or the work actual, the work that actually gets put into this thing, if you will. Okay, so this is what I'm looking for. I know this. How do I find this? So I'm looking for an unknown energy quantity, looking for an unknown energy value. Work is an unknown energy. Now you guys will get, I tell you, you guys will get really tired of me saying, okay, well, how would we find an unknown energy? And I will stare at you blankly until I get an answer I like. And most of the time, the answer I like is the first law. The first law is a very good, powerful tool for finding an unknown energy if I know everything else, right? So if I look at the first law, then the first law has work in it, right? So a simple way of write you can do one of two things with the first law. You can write the big long equation, say, well, that's heat in plus work in plus the energy of mass in minus heat out minus work out minus the energy of any mass going out is equal to m times delta U plus change in kinetic energy, V2 squared minus V1 squared both over 2 plus G times delta Z. So you can write the whole thing out, and then you can cross out the things that you don't need. All right, that's okay. Um, let's assume that it's a really well-sealed car and there's no mass crossing the boundary. Okay. We know it's a level road. So this is going away. If I'm looking for the work in, which is really what I'm looking for here, I'm looking for the work in, I'm going to assume that there's really no work out because there's not really anything doing work out. And then we don't know anything about heat transfer. Here's the dirty little secret is in chapter 2, we can assume that unless the problem is asking for heat transfer or unless it's given to me, I'm probably just going to assume that these are 0 or that we don't have good tools to find them. That stops working at chapter 4. But in chapter 2, it's okay to make that assumption. And the other thing is we weren't given anything about the internal energy. We don't have any tools for that. After chapter 3, we'll have tools to find delta U. So unless the problem's asking for delta U or it's specifically given to me, we're probably just going to assume that that's 0. Okay. So notice what I've got left. Work in equals m v2 squared over 2 because v1 is also 0. It's that simple. I know it's not that simple. Another way you can think about it, a very common thing that we will do the rest of the semester is I'll say, okay, well, how do we write a first law equation? Well, what do? You draw your system. What is my system? I've got this car. Okay? What energy is being added to the car? Well, I've got work in. And what I want to do is I want to find what is the actual minimum least amount of work required to get this car up to speed. That's really all I'm trying to find. So if this thing is losing heat or it's increasing its internal energy, I've got to add additional work to overcome those energy losses or energy changes inside. So I'm trying to find what is the absolute minimum work required. So I'm going to assume that all these other things are zero, and that's the only thing crossing the boundary. That if I can draw my system and draw all the energies crossing my boundary, that represents the entire left-hand side of my first law equation. I don't have to write the whole thing out and cross everything out. If I just look at a picture and say what energies cross the boundary, I just have work in, so that's my entire left-hand side. What energies are changing? Well, again, if I'm given delta U or it's asking for delta U, it's not zero. Or after chapter 3, we're not going to assume it's zero. But for now, those are kind of our main tools. So it's not discussed in the problem, it's not given, so we're just going to assume it's zero. We know all these other things are zero. So that's all that's left. The energy coming in causes the kinetic energy of the car to change. It's basically a physics 1 problem from that aspect. So let's start working it. So the work in, I think I've got all this information, right? I know the mass, I know V2. By the way, let's put this in per hour. Normally, that's not a unit that we're going to work with. So if I take that 328,000 divided by 3,600, that gives me 9.11. So this is the kind of thing I would normally ask you guys to calculate as we go along. So that's 9.11 feet per second, or 91.11. I apologize. Now you can see the number. I said it wrong, but it's on the calculator correctly. Okay. All right. So I'm going to square that. I'm going to divide that by 2 because it's v squared over 2. Now I'm going to multiply it by the mass as 1,800 pound mass. And so you can write that out here if you need to. Kind of in the interest of, well, I guess we could write that. Let's write it out because we need to see the units. 1,800 pound mass times 91.11 feet per second. That's going to get squared and then divided by 2. And so that number is going to come out to be then, you see on my calculator here, we'll get it up here where we can see it. Oh, no, goodness, my bad. I get that glare off it. I apologize. 7,000, 7 million. I apologize. 7,471,000. I'm going to leave it there. I don't care about the other numbers. 3 significant figures is enough. 4 significant figures is excessive. More than 4 significant figures is always wrong. Just almost always wrong. 3 significant figures is enough. You don't know these numbers, right? We don't have any kind of precision up there that would indicate I need to carry more numbers than this. The rookie mistake is to say, oh, that's BTUs, right? No, that's not. That is, let's collect our units. The units are what are here. Pound mass, and I've got feet per second that's getting squared. So that's pound mass, feet squared per second squared. Now, what units would you like? That's always the question. What units would you like? Well, what is it measuring? We're measuring work. Work is energy. I want units of energy. BTUs would be nice, right? BTUs would be nice. Let's see if we can get there. Well, how do we get there? I know if I can get to a unit of force times distance, I know if I can get to units of force times distance, that that I can get that to BTUs, right? Because I know, yeah, so see here, energy, and let's get this, get it under the camera to see energy here, right? I know BTUs is 778.169 pound force feet. So I think we can use that. Right? So let's write it down here. Work in equals this 7471000. This pound mass feet squared per second squared. And I know I can use this conversion factor to get to BTUs. That is, for every BTU, there is 778.169, and that is pound force feet. But notice this is pound force and this is pound mass. These are not the same thing. My alarm told me we're gone 15 minutes, and that's okay. We're going to go over 15 minutes on this video, but it's the last one we're going to do on this, so it's okay. Okay, so again, notice I got pound force here. I do not have pound force here. This is pound mass. These are not the same. And I can't just say, oh, well, doesn't it just cancel out? No, it's the English units. It definitely does not just cancel out. So how do we get there? Well, remember, I said there, and I drew like big stars around it, said if you need to get rid of pound mass to go to pound force, there's this conversion that says for every pound force second squared, there are 32.2 pound mass feet. And that will get rid of the pound mass. That's going to leave me with pound force in the numerator. Second squareds go away. I've got feet squared on top. I've got feet here and I've got feet there. So my feet squared are going to go away. And notice I've got pound force here and pound force there. That leaves BTUs. Okay, so this number divided by 778.169, and then also divided by 32.2. The work in. The minimum work that we would need to accelerate this car up to that speed is about 298 BTUs. All right, are we done? Is that our answer? Well, told you, if you'll make it very clear, what are you looking for? You're looking for the efficiency. Is this the efficiency? No, it's a lot of work to get an intermediate number. Welcome to the rest of engineering. That is we're going to do a lot of work to get something that's not actually what we're looking for, but it's a step in the path to get there. I know now the energy consumed was given to me. I've now figured out what is the minimum amount of work to actually cause this car to accelerate. That's this number here. So that tells me I could figure out the efficiency then based on this 298 BTUs. That's my expected small number. That's the absolute minimum amount of energy required to get this car up to speed, divided by the amount of energy it actually is using to get up to speed. That's 380 BTUs. Okay, and so then you can see that's 298 divided by 380 is about 80%. It's about 0.78, or about 78%. And that's our answer. All right. If you have questions, comments, complaints, be sure and let me know. That basically gets us through chapter 2 with a couple of examples and the basic theory. See you guys next time.